So in this video, we'll start talking about the heap data structure. So in this video, I want to be very clear on what are the operations supported by a heap, what running time guarantees you can expect from canonical implementations, and I want you to get a feel for what kinds of problems they are useful for. In a separate video, we'll take a peek under the hood and talk a little bit about how heaps actually get implemented. But for now, let's just focus on how to use them as a client. So the number one thing you should remember about a given data structure is what operations it supports and what is the running time you can expect from those operations. So basically a heap supports two operations. There's some bells and whistles you can throw on, but the two things you got to know is insertion and extract min. All right, so the first thing I have to say about a heap is that it's a container for a bunch of objects, and each of these objects should have a key, like a number, so that for any given object you can compare their keys and say one key is bigger than the other key. So for example, maybe the objects are employee records and the key is social security numbers. Maybe the objects are the edges of a network and the keys are something like the length or the weight of an edge. Maybe each object indicates an event and the key is the time at which that event is meant to occur. Now the number one thing you should remember about a given data structure is, first of all, what are the operations that it supports, and second of all, what is the running time you can expect from those operations. For a heap, essentially, there's two basic operations: insert and extract the object that has the minimum key value. So in our discussion of heaps, we're going to allow ties. They're pretty much equally easy with or without ties. So when you extract min from a heap that may have duplicate key values, then there's no specification about which one you get. You just get one of the objects that has a tied for the minimum key value. Now, of course, there's no special reason that I chose to extract the minimum rather than the maximum. Either you can have a second notion of a heap, which is a max heap, which always returns the object with a maximum key value, or if all you have at your disposal is one of these extract min type heaps, you can just negate the sign of all of the key values before you insert them, and then extract min will actually extract the max key value. So just to be clear, I'm not proposing here a data structure that supports simultaneously an extract min operation and an extract max operation. If you wanted both of those operations, there'd be data structures that would give it to you. Probably a binary search tree is the first thing you'd want to consider. So I'm just saying you can have a heap of one of two flavors. Either the heap supports extract min and not extract max, or the heap will support extract max and not extract min. So I mentioned that you should remember not just the supported operations of a data structure, but what is the running time of those operations. Now for the heap, the way it's canonically implemented, the running time you should expect is logarithmic in the number of items in the heap. And it's log base 2 with quite good constants. So when you think about heaps, you should absolutely remember these two operations. Optionally, there's a couple other things about heaps that might be worth remembering. Some additional operations that they can support. So the first is an operation called heapify. Like a lot of the other stuff about heaps, it has a few other names as well, but I'm going to call it heapify, one standard name. And the point of heapify is to initialize a heap in linear time. Now, if you have n things and you want to put them all on a heap, obviously you could just invoke insert once per each object. If you have n objects, it seems like that would take n times log n time. Log n for each of the n inserts. But there's a slick way to do them in a batch, which takes only linear time. So that's the heapify operation. And another operation which can be implemented, although there are some subtleties, is you can delete not just the minimum, but you can delete an arbitrary element from the middle of a heap, again in logarithmic time. I mention this here primarily because we're going to use this operation when we use heaps to speed up Dijkstra's algorithm. So that's the gist of a heap. You maintain objects that have keys, you can insert in logarithmic time, and you can find the one with the minimum key in logarithmic time. So let's turn to applications. I'll give you several. But before I dive into any one application, let me just say, what's the general principle? What should trigger you to think that maybe you want to use a heap data structure in some task? So the most common reason to use a heap is if you notice that your program is doing repeated minimum computations, especially via exhaustive search. And most of the applications that we go through will have this flavor. There'll be a naive program which does a bunch of repeated minimums using just brute force search, and we'll see that a very simple application of a heap will allow us to speed it up tremendously. So let's start by returning to the mother of all computational problems, sorting an unsorted array. Now, a sorting algorithm which is sort of so obvious and suboptimal that I didn't even really bother to talk about it in any other point in the course is selection sort. What do you do in selection sort? You do a scan through the unsorted array, you find the minimum element, you put that in the first position, you scan through the other n-1 elements, you find the minimum among them, you put that in the second position, you scan through the remaining n-2 unsorted elements, you find the minimum, you put that in the third position, and so on. So evidently, this sorting algorithm does a linear number of linear scans through this array. So this is definitely a quadratic time algorithm. That's why I didn't bother to tell you about it earlier. So this certainly fits the bill as being a bunch of repeated minimum computations, or for each computation, we're doing exhaustive search. So this, a light bulb should go off and say, aha, can we do better using a heap data structure? And we can, and the sorting algorithm that we get is called heap sort. And given a heap data structure, the sorting algorithm is totally trivial. We just insert all of the elements from the array into the heap, then we extract the minimum one by one. From the first extraction, we get the minimum of all n elements. The second extraction gives us the minimum of the remaining n-1 elements, and so on. So when we extract min one by one, we can just populate a sorted array from left to right. Boom, we're done. What is the running time of heap sort? Well, we insert each element once and we extract each element once, so that's 2n heap operations. And what I promised you is that you can count on heaps being implemented so that every operation takes logarithmic time. So we have a linear number of logarithmic time operations for a running time of n log n. So let's take a step back and appreciate what just happened. We took the least imaginative sorting algorithm possible, selection sort, which is evidently quadratic time. We recognized the pattern of repeated minimum computations. We swapped in the heap data structure, and boom, we get an n log n sorting algorithm, which is just two trivial lines. And remember, n log n is a pretty good running time for a sorting algorithm. This is exactly the running time we had from merge sort. This was exactly the average running time we got from randomized quicksort. Moreover, heap sort is a comparison-based sorting algorithm. We don't use any data about the key elements. We just use it as a totally ordered set. And as some of you may have seen in an optional video, there does not exist a comparison-based sorting algorithm with running time better than n log n. So for the question, can we do better? The answer is no if we use a comparison-based sorting algorithm like heap sort. So that's pretty amazing. All we do is swap in a heap and the running time drops from the really quite unsatisfactory quadratic to the optimal n log n. Moreover, heap sort's a pretty practical sorting algorithm. You run this, it's going to go really fast. Is it as good as quicksort? Maybe not quite, but it's close. It's getting into the same ballpark. So let's look at another application, which frankly in some sense is almost trivial, but this is also a canonical way in which heaps are used. And in this application, it will be natural to call a heap by a synonymous name, a priority queue. So what I want you to think about for this example is that you've been tasked with writing software that performs a simulation of the physical world. So you might pretend, for example, that you're helping write a video game which is for basketball. Now, why would a heap come up in a simulation context? Well, the objects in this application are going to be events records. So an event might be, for example, that the ball will reach the hoop at a particular time, and that would be because a player shot it a couple seconds ago. When, if, for example, the ball hits the rim, that could trigger another event to be scheduled for the near future, which is that a couple players are going to vie for the rebound. That event, in turn, could trigger the scheduling of another event, which is one of these players commits an over-the-back foul on the other one and knocks him to the ground. That, in turn, could trigger another event, which is the player that got knocked on the ground gets up and argues the foul call, and so on. So when you have event records like this, there's a very natural key, which is just the timestamp, the time at which this event in the future is scheduled to occur. Now, clearly a problem which has to get solved over and over and over again in this kind of simulation is you have to figure out what's the next event that's going to occur. You have to know what other events to schedule, you have to know how to update the screen, and so on. So that's a minimum computation. So a very silly thing you could do is just maintain an unordered list of all of the events that have ever been scheduled and do a linear pass through them and compute the minimum. But you're going to be computing minimums over and over and over again. So again, that light bulb should go on and you could say, maybe a heap is just what I need for this problem. And indeed it is. So if you're storing these event records in a heap with the key being the timestamps, then when you extract min, the heap hands for you on a silver platter using only logarithmic time exactly which event is going to occur next. So let's move on to a less obvious application of heaps, which is a problem I'm going to call median maintenance. The way that this is going to work is you and I are going to play a little game. So on my side, what I'm going to do is I'm going to pass you index cards one at a time when there's a number written on each index card. Your responsibility is to tell me at each time step the median of the numbers that I've passed you so far. So after I've given you the first 11 numbers, you should tell me as quickly as possible the 6th smallest. After I've given you 13 numbers, you should tell me the 7th smallest, and so on. Moreover, we know how to compute the median in linear time, but the last thing I want is for you to be doing a linear time computation every single time step. Right? I only give you one new number. Do you really have to do linear time just to recompute the median if I just gave you one new number? So to make sure that you don't run a linear time selection algorithm every time I give you one new number, I'm going to put a budget on the amount of time that you can use at each time step to tell me the median. And it's going to be logarithmic in the number of numbers I've passed you so far. So I encourage you to pause the video at this point and spend some time thinking about how you would solve this problem. Alright, so hopefully you've thought about this problem a little bit. So let me give you a hint. What if you use 2 heaps? Do you see a good way to solve this problem then? Alright, so let me show you a solution to this problem that makes use of 2 heaps. So the first heap we'll call h low. This heap will support extract max. Remember we discussed that a heap you could pick whether it supports extract min or extract max. You don't get both, but you can get either one. It doesn't matter. And then we'll have another heap h high, which supports extract min. And the key idea is to maintain the invariant that the smallest half of the numbers that you've seen so far are all in the low heap, and the largest half of the numbers that you've seen so far are all in the high heap. So for example, after you've seen the first 10 elements, the smallest 5 of them should reside in h low, and the biggest 5 of them should reside in h high. After you've seen 20 elements, then the bottom 10, the smallest 10 should reside in h low, and the largest 10 should reside in h high. If you've seen an odd number, either one can be bigger, it doesn't matter. So if you have 21, you have the smallest 10 in the one and the biggest 11 in the other, or vice versa. It's not important. Now given this key idea of splitting the elements in half according to the 2 heaps, you need 2 realizations, which I'll leave for you to check. So first of all, you have to prove you can actually maintain this invariant with only O of log I work in step I. Second of all, you have to realize this invariant allows you to solve the desired problem. So let me just quickly talk through both of these points, and then you can think about it in more detail on your own time. So let's start with the first one. How can we maintain this invariant using only log I work at time step I? And this is a little tricky. So let's suppose we've already processed the first 20 numbers, and the smallest 10 of them we've all worked hard to put only in h low, and the biggest 10 of them we've worked hard to put only in h high. Now here's a preliminary observation. What's true? So what do we know about the maximum element in h low? Well, these are the 10th smallest overall, and the maximum then is the biggest of the 10th smallest. So that would be the 10th order statistic, so the 10th smallest overall. Now what about in the high heap? What is its minimum value? Well, those are the biggest 10 values, so the minimum of the 10 biggest values would be the 11th order statistic. Okay? So the maximum of h low is the 10th order statistic, the minimum of h high is the 11th order statistic. They're right next to each other. These are in fact the 2 medians right now. So when this new element comes in, this 21st element comes in, we need to know which heap to insert it into. And well, if it's smaller than the 10th order statistic, then it's still going to be in the bottom, then it's in the bottom half of the elements. It needs to go in the low heap. If it's bigger than the 11th order statistic, if it's bigger than the minimum value of the high heap, then that's where it belongs, in the high heap. If it's wedged in between the 10th and 11th order statistics, it doesn't matter. We can put it in either one. This is the new median anyways. Now, we're not done yet with this first point because there's a problem with potential imbalance. So imagine that the 21st element comes up and it's less than the maximum of the low heap, so we stick it in the low heap, and now that has a population of 11. And now imagine the 22nd number comes up, and that again is less than the maximum element in the low heap. So again we have to insert it in the low heap. Now we have 12 elements in the low heap, but we only have 10 in the right heap. So we don't have a 50-50 split of the numbers. But we can easily rebalance. We just extract the max from the low heap and we insert it into the high heap. And boom, now they both have 11, and the low heap has the smallest 11 and the high heap has the biggest 11. So that's how you maintain the invariant, that you have this 50-50 split in terms of the small and the high between the two heaps. You check where it lies with respect to the max of the low heap and the min of the high heap. You put it in the appropriate place, and whenever you need to do some rebalancing, you do some rebalancing. And this uses only a constant number of heap operations when a new number shows up, so that's log I work. So now, given this discussion, it's easy to see the second point. Given that this invariant is true at each time step, how do we compute the median? Well, it's going to be either the maximum of the low heap and or the minimum of the high heap, depending on whether I is even or odd. If it's even, both of those are medians. If I is odd, then it's just whichever heap has one more element than the other one. So the final application we'll talk about in detail in a different video, a video concerned with the running time of Dijkstra's shortest path algorithm, but I do want to mention it here as well, just to reiterate the point of how careful use of data structures can speed up algorithms, especially when you're doing things like minimum computations in an inner loop. So Dijkstra's shortest path algorithm, hopefully many of you have watched that video at this point, but basically what it does is it has a central while loop, and so it operates once per vertex of the graph, and at least naively it seems like what each iteration of the while loop does is an exhaustive search through the edges of the graph, computing a minimum. So if we think about the work performed in this naive implementation, it's exactly in the wheelhouse of a heap, right? So what we do in each of these loop iterations is do an exhaustive search computing a minimum. You see repeated minimum computations, a light bulb should go off and you should think, maybe a heap can help. And a heap can help in Dijkstra's algorithm. The details are a bit subtle and they're discussed in a separate video, but the upshot is we get a tremendous improvement in the running time. So recalling that m denotes the number of edges and n denotes the number of vertices of a graph, with the careful deployment of heaps in Dijkstra's algorithm, the runtime drops from this really rather large polynomial, the product of the number of vertices and the number of edges, down to something which is almost linear time. Namely O of m log n, where m is the number of edges and n is the number of vertices. So the linear time here would be O of m, linear the number of edges. We're picking up an extra log factor, but still this is basically as good as sorting. So this is a fantastically fast shortest path algorithm, certainly way, way better than what you get if you don't use heaps and just do repeated exhaustive searches for the minimum. So that wraps up our discussion of what I think you really want to know about heaps. Namely, what are the key operations that it supports? What is the running time you can expect from those operations? What are the types of problems that the data structure will yield speedups for? And a suite of applications. For those of you that want to take it to the next level and see a little bit about the guts of the implementation, there is a separate optional video that talks a bit about that.